Hello students, in this video we'll begin our discussion about determinants. Let's define determinant of a 2 by 2 matrix as follows. It's going to be AD minus BC. This is the definition of a two-dimensional determinant. Let's understand why this quantity, which inputs a 2 by 2 matrix and outputs a real number, so as a function, this determinant inputs a 2 by 2 matrix and outputs a real number, okay? So what I want to do is I want to make the following claim. So actually they're easy to compute, for example. This is just simply do the diagonals minus the off diagonals. So here's a proposition about determinants, which relates it to the invertibility of the matrix A. So A, which is A, B, C, D, is invertible if and only if determinant of A is non-zero. And so let's prove this. And so to prove this, it will illustrate something we'll see in a further video, this notion of an adjugate matrix. So what I'm going to do is I'm going to define adj of A to be D, A, and then negative B, negative C. This is a matrix. And now let's check. So here's our proof, this is a proof of our proposition. Then A times adjugate of A. Well, let's see what we get. We'll have an A, B, C, D, and then a negative D, a negative B, a negative C, and an A. And so what we'll get is we'll get AD minus BC, AD minus BC, a 0, and an AD minus BC, which is exactly just the determinant of A times the identity matrix. So we have this relationship, and you can check this is also equal to adjugate. They commute with each other, adjugate of A times A. And so now, suppose that the determinant is not equal to 0. So if determinant of A is not equal to 0, then what? Then adjugate of A over determinant of A is equal to A inverse. Great, by this formula over here. And now suppose if A is invertible, if A inverse exists, and determinant of A is equal to 0, so if that was the case, then this relationship over here, that would imply that A adjugate of A is 0. And since A is invertible, I can hit A inverse on both sides, which would say that the adjugate of A is the 0 matrix by taking the inverse of both sides, and that implies that all the integers of A would be equal to 0, that A is equal to 0, which is a contradiction since A is invertible, right? So that shows that this is a necessary and sufficient condition for the matrix to be invertible, is that the determinant is non-zero. So now we'll discuss in further videos the geometry of these determinants, but let's at least sort of illustrate how we define determinants in a higher dimensional setting now. So for a 3 by 3 matrix, I'm going to define this, determinant of this 3 by 3 matrix, A1, A2, A3, B1, B2, B3, C1, C2, C3. And this will illustrate the more general principle. What I'm going to do is I'm going to put a sign on every element in this determinant. So this is going to be a plus, minus, plus, minus, plus, minus, plus, minus, plus. So it alternates. So the number of steps it takes to get back to the 1, 1 entry, so this would take 1 step, so I get 1 negative sign. This would take 2 steps, I get 2 negative signs. It's the number of steps that are required either vertically or to the left to get back to the 1, 1 entry is the sign of that entry. It's the sign of the permutation, the number of steps it takes. And what we're going to do is we're going to expand this along any row or any column using these cofactors. And so what I'm going to do is I'm going to define this in the following way. I'm going to define this to be A1 with a positive sign times the determinant of the matrix that we get when we eliminate the row and column in which A1 resides. So that would leave me with a what? A B2, B3, then a C2, C3, minus A2, and then we're going to look at I'm going to eliminate the row and column in which A2 resides. I'm going to have a determinant of B1, B3, C1, C3, and then finally the plus A3, and then the determinant of B1, B2, C1, C2, okay? That's the formal definition of what the determinant is, but the remarkable theorem, which is due to Laplace, says that you can actually expand along any row or any column. So let me illustrate that by doing a what? So this is going to be expanding along the first row over here. Let's say, for example, we wanted to expand along the second column over here, right? So if we did that, it would be what? If we did the second column, it would be negative A2 times what determinant? Times the determinant, we're going to punch out the row and column in which A2 resides. So I have a B1, B3, C1, C3. So B1, B3, C1, C3. Then I'd have a positive B2 times the determinant of what we get. We punch out the row and column, so I have an A1, A3, C1, C3, A1, A3, C1, C3. And then finally a negative C2 times the determinant of what we get when we punch out the row and column which C2 resides. So I have A1, B1, A3, B3. A1, A3. So row and column, so A1, A3. And then a what? And then a B1, B3. B1, B3. Now we can check over here that what is one common characteristic of the terms in these determinants over here. If we look at this, I have an A1 and then a B2, then a C3. There's a 1, a 2, and a 3 in this one. There's a 1, a 2, and a 3 in this one, a 1, a 2, and 3 in this one, a 1, a 2, and 3 in this one, and a 1, a 2, and 3 in this one. So what I'm really doing here is I'm just doing products of A, B, and C, and I have to have the index 1, 2, and 3 exactly one time, and based on the sign of the permutations, the number of steps it takes to take that I, J, K to get back to 1, 1, 2, 3 to have the identity permutation. That is the sign of what these numbers are. The negatives and positives comes from the sign of those permutations. In further videos, we'll see how to expand this for more general classes of matrices. Thank you very much.